Yes, we were seeing about the different types of curves in the previous class. So we'll just see about a little bit about how these curves vary or change its shape when we change the control point. So first, let us see about for a Bezier curve. Yeah. So for a Bezier curve, if you take up, we have to have four control points. So the first and the last is control point is fixed, and we can move the other two at the same time. And where this curve has got about 50 parts, this curve has been made up of 50 small straight lines. So as we tend to move these control points, yes, according to the equation, the curve is going to change its shape, right? As we can see in the screen, for every position, change in the position of the control points. So now let's see about the Hermite's spline. So here, again, the curve is going to be made up of 50 small straight lines. So it appears to be a smooth curve. Okay, and as we move these control points, the Hermite's curve is going to change its shape accordingly, right? Where it's going to be tangential to the first and this last point, the curve, right? But now, as we are going to decrease the curve parts, we can see that the smoothness of the curve is going to decrease. And here we can see, as it is for 14 parts, it's made up of all small straight lines, which is not going to appear as a smooth line. Okay, right. So here we can see these things, right? So the more it is, the finer it is going to be. The curve is going to be a smoother one, right? And similarly, it's going to be the same thing is going to be considered when it comes up for the surface also. For a Hermite's surface, where we can we can change the shape in U direction as well as in Y direction. Y direction, because the surface will always have two dimensions. So accordingly, it's going to change its uh, surface shape entirely based on the shape of the curve that is going to be there in the U direction as well as in the Y direction. So based on this, and similarly here also we can see, as we change the number of parts, we are going to, the shape of the surface, the finish is also going to be vary. So the lesser the number of parts, the more the rough with sharp edges, turnings it is going to, the surface is going to have. If it is going to have a smoother, more number of parts, then we can look like, it will look like this. It's going to have smooth surfaces, right? Yeah. So this is about the Hermite's curve, where all these complex shapes are being utilized in the various sectors, let it be in the animation field, automobile, aerospace industries, right? So these are very much required to for the generation of surfaces, right? Right? Okay. So now we'll go to the equation part of this. So Hermite's curve. So for Hermite's curve, generally what they do in the CAD software is that, let it be any type of curve, it is going to be restricted to 3 degrees of freedom. 3 degrees. Okay, that is the equation. They don't go on for the fourth or the fifth order, where one curve is going to have a third order equation, the other curve is going to have fifth order equation, and they don't want to have different curves with different degrees of degrees present in an equation. Right? So if they have all of them, it's usually restricted only to third degree, that is cubic, because of the advantage that two curves, when they are represented by the same degree of equation, okay, then its continuity is going to be easier, and the second derivative is guaranteed to at the connection point. So it will appear as a very smooth continuous curve rather than having it in the form of split ups, right? So one will be having a smooth curve and then from the next connecting point, the next curve will have like this, then it's not going to look good. So uniformity is going to be maintained. That is why it has been restricted to the degrees, or degrees is going to be only 3. If there is going to be higher than 3, there is a problem of computation. No, there is nothing that is going uh, to be that the curve is not going to be represented in a much more smoother manner. But the problem is that it is going to have heavier computation once the equation degree goes beyond 3. Okay. Now coming to the simplest parametric equation. Now for a particular point P in the u direction, we can have, it will be of x value in u direction, y and z. Okay, and where it's going to have its vector coefficients a naught, and for the y a1 u, and the next one a2 u square, where the values is going to be 0 to 1, right? So the value of u is going to vary from 0 to 1. So this a naught, a1, a2, and a3 are the vector coefficients for the parametric equation. Okay, that is uh, for this particular equation shown over here. Okay, and the row vectors with xy components with xyz. Okay, and the coefficients are algebraic coefficients, and change the curve shape cannot be intuitively anticipated. That is, we cannot identify it clearly once they change its curve shape. What is going to be the change if we are going to vary these algebraic coefficients? So to avoid this problem, we have to get it into geometric meaning, right? So we have to convert this algebraic coefficients into geometric meaning, so that if we get this geometrical data, then we can find out, or we can assess the shape of the curve. So for this, the position vectors of the two end points of the curve, that is P0 and P1. For a Hermite's curve, we will have the first point and the last point. So this will be the P0 and this will be the P1, where for the Hermite's curve, a tangent has to be drawn over here and here. Okay, so this is going to be P0 dash, and this is going to be P1 dash, right? So for this, the tangent vectors at the endpoints are required, okay, which is going to be represented by P0 dash and P1 dash. Now imposing the boundary conditions with respect to using this equation that we have seen over the parametric equation over here, right? So with this, we can come out with the values of what is the value of P0 and P1. We can come out with a generalized equation where P0, as we know, the u value is going to vary from 0 to 1. Okay, and once when we substitute the value of u to be 0 over here, okay, so one thing is that we will be able to get P0 once at the value of z, the value of 0, it's going to be only a naught. That is when we are going to substitute P of 0 over here. So u value is 0. So this is going to be 0, here also 0, right? Okay, and thereby what is going to happen? Sorry, this has to be a plus sign, and this is also going to be 0, right? So thereby it's going to be only P of 0 is going to be only equal to a naught, okay, which is the vector coefficient. So similarly, when we start substituting the value of u equal to 1 in this particular equation, okay, now what we'll get, P of 1, that is at the end point, whose value is going to be 1. Okay, so a naught, u value is 1, here also 1, and here also 1. So we'll get a naught plus a1 plus a2 plus a3. Now when we go for the boundary conditions, okay, when you start substituting this, okay, when you take the derivation of this, P naught dash is going to be P dash of, for 0 value is going to be A1. And similarly, when we take the derivative of this, okay, it is going to be P1 differentiation for value of 1, it will be A1 plus 2 times A2 plus 3 times A3. Now, this equation can be solved, okay, where, so what is the value of this? A naught is going to be equal to P naught, right? And A1 is going to be P naught differentiate, the first order differentiation, P naught dash, right? And subsequently for A2, the value is going to be minus 3 P naught plus 3 P1 minus 2 P naught dash minus P1 dash. So the value of A3 is going to be 2 times P naught minus 2 times P1 plus P naught dash plus P1 dash. So these are the uh, on on solving this, we get these terms for the A naught, A1, A2, and A3 values. Okay. Now with this, what is going to happen when we substitute these uh, equation of 6.12, that is this particular portion, in the generalized equation, we are going to get this uh, equation over here, the final ultimate equation in a generalized form for the Hermite's curve. So P of u is going to be equal to, in brackets, when we write it up in matrix form. After solving, they converted it into matrix form so that it's easier to write these equations. So it's going to be the first matrix 1 minus 3 times u square plus 2u cube, right? So that is one set. Okay, then the next one is going to be 3 times u square minus 2 times u cube, and then it's going to be for u minus 2u square plus u cube, and last one u square, sorry, minus u square plus u cube, because we have totally p naught, p1, p naught dash, and p1 dash. So for all these things, when it is going to be multiplied with this, right? So the first one over here multiplied by the first matrix. So here, I mean the first one, the second set, the third set, and the fourth set, right? So that is why we have it like this. So it should, we can also write it as one below the other, so that it's easy to multiply. Right. So now with this, the curve equation no longer includes the algebraic coefficients. So it's going to be having the geometrical coefficients, which is which is the Hermite's curve. So with this, we can go about with finding out the shape of the curve, which is manageable. The advantage of this is that we can anticipate, that is, we can guess the curve, how it is going to change once these control points are going to be changed, right? So we can modify, we can shift it, right? And all those things can be performed. So yes, so next is that here there is one particular thing where they have gone with this particular uh, writing the equation for, I mean the graph for this Hermite's curve, right? Okay, so here they are going to take the geometrical coefficient to be as b, and whose matrix, which as we just saw, for the first one it's going to be 1 minus 3u square plus 2u cube, and for the second one function it's going to be 3u square minus 2u cube. The third function u minus 2u square minus u cube, and finally for the fourth function it is going to be minus u square plus u cube, right? So with this, so these two are going to be the, it's always going to be in a particular order, where this is going to be for p naught, and this is going to be p1, and this is going to be for p naught dash, and this is going to be for p1 dash, right? So always the last two rows are meant for the derivatives. right? Whereas the first two are meant for the starting and final points of the hermite curve. Okay. So now, so this is the first, yes, that is what has been indicated, specifying the first row is for P naught, the second row is for the P1, third and fourth is for the derivatives of this. Right. So with this, the effect of tangent vectors on the curve shape can be, we can see it over here. We'll see that in the graph which is below, right? And the changes and the magnitude of the tangent vectors and their directions are held constant over here. So conclude that the magnitude and the tangent vector determines how far the effect of these tangent vectors would propagate towards the center of the curve, right? So where P1 dash affect the shape of the curve with relevant uh, importance determined over here as per the function, right? So we'll see here for the graph that just mentioned. Just a second. Yes. So for a particular thing where we have the starting coordinate to be 1, 1 and the last coordinate is going to be, that is P1 is going to be 5, 1, which is the coordinate of the control points. Therefore, that is the first and the last. And yes, so when we start doing this with respect to these equations and drawing the tangents for this, we get these various shapes of the curve. Okay, so as we are going to see for the p-value here, if we take up this particular thing, especially the last one, it is going to be 13, 13 and 13 minus 13. So we're going to twist and take a turn over here, right, at the highest point. Right. Right. So yes, so this is about the Hermite's curve, where this equation especially this is going to be where it will have the curve in the form of in u, x, y, and z directions, which is necessary, right? So as we can, because the curve, though it is only any type of curve, whether it's Hermite curve or Bezier curve, it need not have to have only in, even though it doesn't have any thickness, the curve or the has no thickness, it can be represented on a 2D surface by making use of 1D representations, which will look like 3D in nature, right? So the 2D is nothing but the sheet of paper or the plane on which we are going to write the curve. The 1D is nothing but the line or the curve that is being used to draw the geometry, and 3D, right? So it has got a maximum control of making use of these lines. We can represent a 3D object, right? We can represent a 3D object in nature, that is onto the sheet of paper or through the representation means, right? So all these curves have this nature of on a 2D script where we can make use of a 1D and represent three-dimensional things, right? So because of this only, we are going to have for everything in X, Y, and Z directions, right? So say for example, if we take up okay, X, Y, and Z direction, I can have this curve to be represented in three-dimensional space. So we are writing this X, Y, and Z coordinates on a 2D representation platform. Okay, the curve used is only a 1D, but ultimately when we draw, it can be indicating in a three-dimensional space where each point on this curve has got a value of x, y, and z directions, right? So if you look at this, this is almost very close to the YZ plane, okay, but it takes a turn, moves towards the XY plane, right, and then comes back towards the ZX plane. So it's going to be three-dimensional form where it's going to be uh, giving us the three-dimensional appearance. So that is why these curves have got these things, right? Right. Second. Right. Right. So this is about the hermite curve. Yeah. And we have seen in the previous classes about the Bezier curve also. Okay, so coming to the evaluation of the Bezier curve, when we represent these curves, the equation is going to be very much important. Okay, and if these curve points are not calculated efficiently, then the curve is going to go wrong. Where ultimately, where we are going to use this for the generation of surfaces, and everything will go wrong, where we will not be able to get the desired shape. Okay, and uh, so these coordinates has to be calculated correctly, let it be for a Bezier curve or for any type of curve in this matter, because all these are based on the mathematical equations. So how far these equations are going to be, the parametric values are to be are important. Smaller intervals to be there so that it's going to be more efficient. Okay, so the Bezier equation, especially where it varies from I to n, that is the starting value to ending value. I is equal to 0 to n, that's 1. Okay, where the blending function should also be taken into consideration. Right. Yeah, right. Yeah, right. So we'll stop here for today. Okay.